בקיצור. Elon Lindenstrauss is currently undergoing the phase transition from Hebrew University to the Institute. A phase transition, but keeping also Hebrew University. I'm not leaving the Hebrew University. It's been a great conference. It gives a panorama of the many interests of Peter and how they're all interconnected. The previous speakers have set a very high bar, and I hope to meet it to the extent that I can. It's also what I'm going to talk about are some things that my colleagues and I have been thinking on for many years, and we've sort of managed to achieve some of the aims we started with. And I'm sort of hoping that in this kind of diverse audience, maybe there would be someone who might find some unexpected uses for the results I'm about to present. So the starting point is a very remarkable theorem of Ratner. So I'm taking G to be a linear algebraic group. In this talk over R, but actually the juicy applications are often over the p-adics or as arithmetics, or if you're fancy, Adels. Gamma is going to be a lattice. And the main hero of the story is going to be a one-parameter subgroup, a unipotent one-parameter subgroup. So I'm going to take, so linear algebraic group is in particular a group of n by n matrices. It has a Lie algebra, and you can take elements of the Lie algebra matrices. So you can take a nilpotent matrix in the Lie algebra, and then take X of SU. This sort of looks like an exponential map, but of course it's a polynomial map because I took U to be a nilpotent matrix. And this is a one-parameter unipotent group. And then, in this level of generality, Marina Ratner proved a remarkable theorem. So here's the theorem. For any point G inside G mod gamma, and the important word here is any, not almost any, any. And nice test function F. So maybe a nice class to take are bounded continuous functions on G mod gamma. I take these an ergodic average, so I'm going to average along a long unipotent orbit, starting from my point G. And this would converge to the average of F over some periodic orbit. So, well, L is sort of the smallest group. L contains my acting group. Of course, it's contained by G. It's smallest. So that this orbit of my original point that I started with is periodic. Now, if I have a flow, an action of R, everybody agrees what periodic is. For more general groups, there's less of an agreement, but I'm in a position to impose the rules. So here's the definition. LG is periodic if the stabilizer of my point G in L is a lattice in L. So it's discrete, and what's more important for us, finite covolume. And this definition of periodic is very nice, but it's sort of, just be careful, periodic could still be unbounded if you have, and I mean, that sort of can happen for semi-simple groups. Ratner proves this remarkable theorem. This is the theorem of Ratner. By combining two ingredients. So she proved the measure classification result, and then she had to somehow tie the measure classification result to the behavior of individual orbits. And this requires, in particular, using important non-divergence estimates by Dani and Margulis. A very useful variant of Ratner's work is due to Shah, so let me talk about that. So for this variant, I need some kind of extra player to help this unipotent group. So I'm going to also have a one-parameter unipotent, a one-parameter diagonal group. So A is now a semi-simple element in Lie algebra. But it's not just any one-parameter unipotent group. So I'll say that AT matches my one-parameter unipotent group US if you could find some third element in the Lie algebra so that U, V, and A form an SL2 triplet. Okay, so in particular, so A, the commutator of A and U is going to be U, the commutator of A and V is going to be minus V, and the commutator of U and V is going to be 2A. That's sort of normalization that I like. And this implies in particular that if you conjugate my unipotent element by my diagonal matrix, I'm getting the same, an element of the same group, but the parameter is now rescaled by a factor e to the t. These are the normalizations that I like. And also, if you have such a situation, and there will be some group H which contains both, containing both US and AT, which is locally isomorphic to SL2. So basically, either SL2R or PGL2R. So this is important for Nimish's result, and the Jacobson-Morozov theorem, which is was Marina's Ratner favorite result about Lie groups, says that any semi-simple group that for any one parameter unipotent group in a semi-simple group G, you could find a matching diagonal group. So of course, not true if you look, for instance, at a group like SL2R semi-direct product R2. And now I can state Nimish's theorem. It's also about long unipotent trajectories, but there is a twist. So now I'm going to take again a point G in G mod gamma, and I'm going to again take a unipotent average, this time over an interval of size 1, but then I am expanding it by some large diagonal matrix. So now this average of size 1 is actually an average over a unipotent trajectory of size e to the t. Okay, so I have done it because of this commutation relation. This average of size 1 becomes now an average on a unipotent orbit of size e to the t. And again, this converges to the average of f over some periodic orbit. But this time, the restrictions are different. So L is the smallest group, again, sandwiched between G, but this time the bigger group, SL2R or PGL2R, as the case may be, such that LG is periodic. Now Nimish Shah proved his theorem by applying Ratner's result, but you could go the opposite way. In sort of the language of analytic number theory, I would say that Shah's result and Ratner's result are elementarily equivalent to each other. Or at least effectively equivalent to each other. And aside, maybe it's interesting to note that one of the early, and maybe one of the most surprising applications of Ratner's theorem is actually due to Mark Burger and Peter Sarnak, which connects the automorphic dual of a Q group, those representations that you actually see in L2 of G mod gamma for all of the congruence subgroups of my congruence lattices of the group G to the automorphic dual of its subgroups. And that sort of, when people talk about property tau, they, without knowing it usually, are using this Burger-Sarnak application of Ratner's theorem. The subject of today's talk are quantitative versions of Ratner's equidistribution theorem and Shah's theorem. But before maybe I'll talk about what we did, let me talk let's start with the first quantitative result about unipotent flows that I'm aware of, and I think that came very early on in the theory of unipotent flows, and that's a theorem by Peter. So in one of his first papers, Peter proved the following result. And I'm omitting some fine print, so it's not, maybe, okay, there's some fine print I'm omitting. It's not literally correct. I'll say without writing what the fine print is. So suppose I have gamma inside SL2R as a lattice, and the interesting case for me is a non-uniform lattice. And suppose, and inside SL2R there's basically only one unipotent group. So this is my one parameter unipotent group. And I will take, and I'm going not to look at every point, but at an explicit collection of points. So I'm now going to take G, which is UT periodic of period capital T, which you should think of as being large. Okay, so I have a large periodic orbit of unipotent flow. And I'm integrating some nice test function, smooth, compactly supported test function along this periodic orbit. I'm taking a complete periodic orbit, that's important. And I'm comparing it to the average of f of G mod gamma. And what Peter proved is that this decays like t to the minus 1/2. So you basically have a square root cancellation. You have an average of something of size t, and the discrepancy is of size square root. Now, what is more, I should also say that, and I'm not exactly sure about the timeline that Don Zagir also has a paper around the same time sketching very impressionistically the same result or a similar result. And what both Sarnak and Don Zagir noticed is that if you take gamma being SL to Z, for instance, if gamma is SL to Z, this square root cancellation, which is in any kind of reasonable, unless some miracle happens, if you have some kind of average, dynamical average, the best one can possibly hope for, if you're sort of being the sharpest possible, is to get square root cancellation. You never get better than square root cancellation unless something very special happens. Well, here something very special happens. The Riemann hypothesis is equivalent to error term being significantly better than square root cancellation. That always seems to me the least promising avenue of attack towards the Riemann hypothesis, because just to get sort of the trivial thing, just to get prime numbers here, you already have to get square root cancellation. But to add, maybe we had a nice mentoring panel yesterday to add my 5 cents, and this is an advice not to advisors, but advice to students. If somebody tells you that this or that might be a good idea how to do something, listen very, very carefully and try to make it work. If somebody tells you that something won't work, take it as a challenge and try to do it anyway. Okay. So
that observation, second part is definitely Zagier before.
Okay. Now, this case of this one parameter unipotent subgroup inside SL2R mod gamma is what's called horospheric. That's sort of a special kind of unipotent group. It's a special case. So I talked about one parameter unipotent groups, but of course one could also talk about higher dimensional unipotent groups, and similar results would hold. A group U is horospheric, so let's get another definition. So I have a subgroup U inside some bigger group G, which maybe you should think of as being a semi-simple group. And this is horospheric if there is some element A in G such that U is precisely the elements of G, so that A to the minus n GA converge to the identity. Okay, I mean, obviously any element that you could conjugate to be close to the identity would have all eigenvalues once, would be unipotent, but not every unipotent group is of this form. And the horospheric case is significantly easier. It was actually proved before Ratner proved her general result. And the first result, equidistribution result for horospherical groups, was by Furstenberg, who considered compact quotients of SL2R. And then I think roughly at the same time, but a bit later than when Peter proved this result, Danny and Smiley showed that unless an orbit is periodic, it will become equidistributed. And what is one notable difference between the Zagir paper and Peter's paper is that Peter was clearly very much aware of what's happening in the homogeneous dynamics world. But in any case, you're not going to get super sharp optimal rates with that, but it's not so hard to quantify equidistribution of horospherical flows. So this has been understood already for some time. There are sort of many, actually quite interesting papers about it, and because there are many, I decided, even though maybe I decided to just not give a full reference because there's sort of quite rich literature on this subject. But the horospherical case has been understood quantitatively. Results for some time, maybe notably by Mark Burger and Kleinbock-Margulis, also. So I'm saying Kleinbock-Margulis, but in fact, this is sort of outgrowth of Margulis' thesis. And others, sort of one, Schlamini-Forni, and many others. Stromberg's on my former student, Safkat, many, Taylor McAdam, many people have interesting results in this direction. So let me explain why the horospheric case is easier, because this picture is a picture I found useful in many situations. And I'll just talk about the case of SL2R modulo gamma, but sort of the picture is a general picture. So it's easy to quantify, or at least you could outsource this to people doing representation theory. The rate at which these ergodic averages that we care about converge to the average of F in, let's say, L2. Okay, point was behavior for every point is what this whole discussion is about. Not almost every point is what discussion is all about. But if you just want to see how close this converges to this in L2, well, you just make a calculation on the relevant representations. Like I said, people understand automorphic spectrum. You know which representation occur. You could estimate this very easily. So that's easy, but it doesn't give you any information about any particular point. So how do you get information about particular points? So here is sort of an important observation, which you could prove by complicated calculation, but you should prove not by complicated calculation, but by picture. But anyway, this is what happens. So take 2 points x and x prime. They might be far away in G mod gamma. You apply this matching unipotent orbit, diagonal orbit, and you get 2 points. You go backwards in time, t. Okay, if x and x prime, if a minus tx prime are close, and if you want a qualitative statement, then you say it's more closer than epsilon. If you want a quantitative statement, then you say closer than e to the minus t over 100 or something. But if these points are close, then you look at the distribution of orbits. So you look at these two probability measures you get by averaging over an orbit. Delta AT delta US. And the probability measure you get by averaging on this other orbit, they are very close. So it's not true. I mean, even the original points might be far away. And even if they were close, they are not going to be sufficiently close that you could apply this big element of the unipotent group and still get things which are close. You would actually see, if you'd follow the trajectory, you would see that one of them would get a bit further along than the other, and you have to compensate for that. But with mild time change, you could match these two orbits so that they are essentially cover the same points, roughly the same speed, and therefore the ergodic averages of this point and this point for any reasonable test function f would be very close. So I care about my original point. I don't know anything about my original point. I look at all the points which are close to a to the minus tx. There are many points of them. One of them would satisfy the typical behavior. And then this one of them that satisfies the typical behavior is enough to tell you that my original point satisfies what I want. And if you get bored during my lecture, I let you think for a minute what goes wrong in the case of a periodic U orbit, because a periodic U orbit does not equidistribute. So you need to think for a minute what goes wrong in the proof I sketched for that. For such a point.
Elon, I think I understand what you're saying here, but can you just check all the primes real quick? Like, I think there's two primes at the top and then missing primes.
Too many primes. I think now I move the prime from here to here. I think now it makes sense. So why are these two things close to one another? If you take, for instance, if you take the case of SL2C, which is the case I'm going to talk about next. So you take 2 points which are nearby. You do this back. You'd actually get one parameter unipotent trajectories which are in a different direction because there's this small. You could sort of maybe. They might differ in the compact part of the diagonal, and then suddenly a unipotent orbit would go in a different direction. So this matching feature is sort of very much, this fact that I told you that these are very close is very much because I'm taking an average over a horospherical group. Otherwise, it's not true. So the non-horospheric case is harder to quantify. There's sort of interesting results in many cases. I'll sort of won't mention all of them, and even those that I mentioned, I'll sort of just give the names. Effective equidistribution is harder. Has been open for some time. So there's some nice, actually more than nice, there's sort of some very important works in that. So one direction was started by Strombergson using analytic techniques, and then Strombergson with Vische, and then Wu Yeon Kim was a graduate student, and sort of again also some related works by Forney and other people. So they were studying skew products like SL2R, semi-direct product R2, when your group is sort of horospheric in the semi-simple group, but in the bigger group, it's no longer horospheric. So that's one direction, and sort of this has quite nice applications. It's related to this behavior of square root of n mod 1. Okay. Now there's also important work which I think has not been sufficiently appreciated by Einzidler, Margulis. There are two papers, so to save Shock, I'll put here Mohammadi in parentheses, not because he's less important, but because I'm talking about two papers. One of them he's a co-author, and one that he's not. So I'm just saving Chok and Venkatesh, which deals with, and also the forthcoming paper by Andreas Wieser, another impressive young mathematician, that deals with periodic orbits of semi-simple groups. A bit like Peter's result from the 80s, you're not talking about orbits of an arbitrary point, but points which have but periodic orbits of some simple group, how the full periodic orbit behaves. There are some results on random walks which don't seem to be so much related, but maybe after Simeon's talk yesterday, they sort of did appear in the same, these two contexts did appear together in Simeon's talk. So anyway, the ideas from those works were relevant to what we did. So the random walks on torus. So you take a torus and you apply randomly two matrices or something. So there's results by Bourgain, Fuhrman, Shachar Moses, and myself. And there's sort of very beautiful work by Wei Kun He and Nicolas Desax. But for the, let's say, the context that is maybe the most classical, which is looking at non-one parameter unipotent groups on quotients of semi-simple groups, very little was known, not even any kind of effective equidistribution results was not known, regardless of rate. And then Amir Mohammadi Zhiren, Wang, and myself, we were able to prove a quantitative equidistribution result. Like I said, there is this Ratner's equidistribution theorem, and there's the Shah's equidistribution theorem that are sort of effectively related to one another. And in the in the qualitative world, historically, what happened was at first Ratner proved her result, and then Nimish proved his. But here in this quantitative world, it's actually more natural to start with the Shah result. So I'm going to just say this effective version of Shah's result. So you take G to be maybe the simplest semi-simple groups beyond SL2R. So there's sort of two candidates fighting for this title. and so we treat both of them. Over the complex numbers, somehow they are the same group. So SL2C, which I think of as a real group for all its matters, and SL2R modulo SL2R, gamma and G, an arithmetic lattice. Irreducible or otherwise, could be reducible. Of course, reducible just talks in the product situation, whether it's essentially a product of groups or not. And I'm taking UT, a one parameter unipotent group, sort of the interesting one parameter unipotent group. In this case of SL2R and SL2R, you could take a one parameter unipotent group that lives on only one factor. That's again a horospheric case, which I've explained to you how one could get a quantitative equidistribution relatively cheaply. And I have some function f, test function. And then and of course a matched diagonal element AT, and there's SL2, a subgroup locally isomorphic to SL2 contains them. I guess in these cases are actually SL2. So if I want to look at the ergodic average, zero, 1, and I compare it to the average on G mod gamma of F. So this is up to some constants which are absolute, and some Sobolev norm of F, nothing too bad, probably one derivative would be enough. You get some kind of polynomial or exponential saving depending on whether your parameter is t or e to the t. So I should say, you should think of this R as being a small, maybe t over 100 or something, but it's a parameter you can play with. Okay, unless there sort of has to be, like in Shah's result, maybe I am on a periodic orbit of, in this case, the nice thing about Shah's result, there's only one thing I need to worry about in this small groups, and that's a periodic orbit of SL2R. So unless, but now, so gamma is effectively computable, though we didn't do it. Basically, depending on the spectral gap in G mod gamma, and like Peter said, unless something bad happens, what is going to be the effective way of saying that I'm not on a periodic orbit? Of course, I can't just say I'm not on a periodic orbit, because this is the result about a fixed finite orbit. If I'm sort of change G by so little that this whole orbit won't change much, I'm not going to change the average. So I need to have a slightly robust form of saying that I'm not on periodic orbit. So unless there exists a periodic H orbit, let's call it H to 0, with, okay, you could measure, basically a periodic orbit comes from some Q group. This Q group has some height, so you could look at the volume. It's sort of, all of these are the same, and I think, Gopal sort of, when I want to try to understand the relation between height and volume, sort of, one looks at Gopal's papers. unless there is a periodic H orbit with height, let's say, bounded by e to the r, and such that if I would look at this whole, my periodic orbit, my orbit and how far it is from this periodic orbit is less than e to the minus r for all tau less than t minus some constant times r. Okay, so basically, unless up to not quite the end, but almost the very end, my orbit is completely trapped close to a periodic orbit of low height, I would get this equidistribution. And you have a freedom to play with this R if you want R to be, if you want the best rates of equidistribution, then you could take R to be essentially T or some absolute constant times T, but then you have to somehow convince yourself that your starting point is not next to any one of a long list of periodic orbits. Or you could be lazy, you could say, I don't really care how good the equidistribution is, but I don't want to work very hard to fight periodic orbits, and then you could take R to be some tiny thing, maybe even sublinear in T, and then you have to worry about much fewer periodic orbits. So there's an interplay here, but basically it's a polynomial type of, it's a polynomial in the orbit power saving. So it's a power saving in the size of the orbit. Now, in work which we are currently writing down, actually fairly good state, in new work, which is now joined also with, so it's Amir and Zhiren, and also Lei Yang and myself. We we prove the same result. So basically, it's exactly the same theorem for some further groups. So basically, for G, a split simple group of rank 2, and U, the generic unipotent. Okay, there are sort of finitely many conjugacy classes of unipotent one-parameter groups, and one of them is sort of more is generic. So for SL3R, we're talking about this group in SL3R. The other simple rank 2 groups are SP4 and G2. So these are also covered by what we are doing. And I would like to mention, if I mention Lei Yang, so in fact, the first result on SL3 is not this, but the first result in SL3 was by Lei Yang. So in SL3, there are sort of two types of unipotents. One of them is generic unipotent, the other is a singular unipotent. And what Lei proves is basically a similar kind of average. So you have a matched diagonal group for this. It's actually the same as a matched diagonal group for this one parameter group, but the scaling is a bit different. So just G. So this is decays exponentially unless, and here sort of G fails to satisfy some explicit Diophantine condition. So that's also an important result. In all of these cases, by Margulis arithmeticity theorem, so gamma is automatically arithmetic except two cases. So maybe I'll write this down. In all these cases, gamma is automatically arithmetic except the SL2C case or the reducible lattices in SL2R times SL2R. Now, what can happen, so let's maybe, so this case of non-arithmetic lattices in SL2C is quite important. It relates to hyperbolic three manifold. That's sort of a very important subject. So let's give this, so if gamma is in SL2C not arithmetic, what can happen, so there you have, like I said, one obstacle to equidistribution is if you have a periodic H orbit, periodic SL2 orbit, then, and you're very close to it, then that sort of can become an obstacle to equidistribution. In the qualitative world, there's another thing that can annoy you. So in this case, you can get, and this actually happened, this is sort of the original examples of non-arithmetic, not sure if they're original, but sort of the famous examples of non-arithmetic lattice by Gromov, Vitetsky, Shapiro. This certainly does happen. One can get H orbits, such that the stabilizer in H of X inside H is Zariski dense, but not a lattice. So this orbit is not periodic, but still somehow it comes back on itself many times. And if it's almost a lattice, if this thing is almost a lattice, then you sort of, you can't expect to get as good error rate as you would like from the general result. So this is this is sort of the obstacle in extending, was the obstacle in extending a result to the non-arithmetic case, at least in SL2C. And somehow very recently, Henri Solan, who's in this audience, proved the following beautiful result, that if gamma in SL2C is a non-arithmetic lattice, then there exists some delta, unfortunately ineffective, such that the critical exponent of stabilizer in H of points X is less than 1 minus delta for all non-periodic. Hx is non-periodic. So there are only finitely many H-periodic orbits in SL2C modulo gamma. That's actually also a beautiful recent theorem by Fisher, Bader, Miller, and Stover, and by Margulis and Amir Mohammadi. But in fact, you get this kind of gap result, a new gap result for Kleinian groups. And this implies effective equidistribution of one parameter in important groups, also in the non-arithmetic case, with a power saving that's unfortunately ineffective. So this implies quantitative equidistribution of
What is not effective?
there is this delta is non-effective. The rate is non-effective. It's sort of by it's essentially by a flexible version of this Bader, Fisher, and friends paper. So if there was a sequence of these with deltas going to 0, then you could somehow get that the lattice was arithmetic. So quantitative distribution here is in SL2C modulo gamma with power saving, but rate which is with power saving, but the rate is not effective. Even the exponent is not effective. And depends on the lattice in ways which we don't understand. I would also say that there are also p-adic versions. So initially, we were relying on some projection theorems which were very much Archimedean in nature, but this has fortunately changed. There are sort of p-adic versions in progress. I'm not sure exactly the status, but basically there's no obstacle to proving p-adic results. And sort of the people responsible for this, I hope I'm giving the right attribution, is Ben Johnsrud and Zhu Lin. So that's another exciting development. Okay, so I have, so like I said in the beginning, these are theorems that we sort of worked hard and we're proud of, but one of my aims in giving this talk is to, in the hope that somebody would find some exciting application for these results, but actually there's sort of one application I would like to present to you, which is again connected to things Peter has worked on. But let's start with Margulis. So in the mid-1980s, it's not entirely clear to me the precise date, in part due to the idiosyncrasies of publishing under Soviet rules, especially if you are not in favor of in the good books of the administration. So in the mid-80s, independent of Ratner, and before Ratner proved the equidistribution results, Margulis used unipotent flows to prove the longstanding Oppenheim conjecture. Used unipotent flows to prove the following beautiful result. So this is a theorem by Margulis, universally known as Oppenheim conjecture, which says that if Q, and this was an open conjecture for maybe 50 years when Margulis proved it. So if Q is an indefinite quadratic form, in at least 3 variables, and not proportional to an integral form, then you could just look at the values this form attains at the integer points, then this would be dense. Okay, that's sort of the theorem. It's of course not true for integral forms, because then you have a discrete set. Also not true for d equals 2. It's related to Markov spectrum and another subject that Peter has contributed a lot to. So, for instance, you could look at something like this form. This form, if you look at the values attained as the integers, will have a gap around 0, which is not allowed. And it's easy to reduce to the d equals 3 case by just passing to a rational subspace. So let's talk about the d equals 3 case. At least, maybe not for the more finer questions that I'll talk about in a minute, but certainly for this initial result, it's easy to pass to a ternary case. An effective version of this was given some years later by Margulis and myself around maybe 10, 12 years ago. What we showed is that if you take the integers and intersect them with a ball of radius t, that this finite set is 1 over log t to some power, and of course not 1, but some constant 1 over log t to some t dense in the interval x less than, again, some constant log t to some power. This was what was we worked to prove in the case of some 10 years ago. But now we have something we can do better, significantly better. So let me give you a theorem. Now this theorem is being written. I hope I'm not missing some condition before you prove the Riemann hypothesis, use it, or whatever, base change or whatever. Double check that I haven't missed something, but I think it should be roughly correct. So this, I should say, this theorem is sort of as follows. Okay, so the history to the theorem, but I'll start with so let me begin with, so let's look. We have a ternary quadratic form. We have two numbers, alpha and beta, and we have t. And this will be just a number of integer vectors inside a ball of radius t, so that q is between alpha and beta, right? So this is some kind of not completely obvious. So this is some kind of shape in 3 dimensions. You take a sphere, you intersect it with the area between two hyperboloids. And so maybe, right, this is, right, this is just the shape inside this ball and between these two, the quadratic form being between these two values. And what you would, a reasonable guess is asymptotically nq alpha bt should be roughly the volume of this set. If you have, sort of in geometry of numbers, if you have sets, you sort of hope that the number of integer points in the set is roughly the volume. And then after you show that, you start to wonder what the error term is. Now, it's far from true if q is integral. I mean, if q is integral and alpha and beta don't contain an integer between them, then certainly you don't have the amount of points you want. But it's actually, there's another even somehow more serious problem. Is integral or proportional to integral, and certainly this is false. A, because of discreteness. But B, you could have way too many isotropic vectors inside in a ball of size t. Instead of having t, you could have something like t log t. So the size, I didn't say that this volume, so basically, if I just look at the ball of radius t and I look at the values q attains there, it will be any number in an interval of size something like t squared. So this volume is easy to see is some constant times t, or asymptotically a constant times t. But the number of isotropic vectors for rational forms could actually be much bigger. So that's sort of an obstacle. And if you are, as pointed out in the paper of Peter, if you are, you could get a dense G delta set of quadratic forms, of irrational quadratic forms, which are so close to rational forms that this kind of asymptotics won't hold. So you need to make some allowances for that. So this problem of trying to understand this number was initially investigated, a lower bound, a tight lower bound, but non-quantitative or maybe quantitative but non-effective on this number. Was given by Dani and Margulis using Marina's equidistribution results. Then Eskin, Margulis, and Moses gave the right asymptotics to this value, but initially only if Q has signature PQ, except the case of 1, 2, and 2, 2. And then in a follow-up paper, they sort of also handled the 2, 2 case, prompted hard by Peter, and extending a result of Peter. Under Diophantine, some Diophantine condition, not because they didn't know how to do it without this Diophantine condition, but because this Diophantine condition is necessary. Otherwise, it's just the result is not true. Now, I think at that stage, Peter stopped pressuring Eskin, Margulis, and Moses to prove results of this type. It had to wait for some time. There's sort of there's some non-trivial issues involved, and until so very recently, the case of ternary quadratic forms, the asymptotics under the Diophantine condition was very recently proved by Wu, Yeon, Kim, already mentioned in an important result in a completely different direction, sort of impressive.
It's one person.
Hmm?
It's one person. Woo-Yeon Kim is
Yeah. It's one person, but sort of the number of people with last name Kim is probably half the population of Korea. So, yeah. One person, many results. Anyway, so let's talk about what we did. And unfortunately, oh no. Anyway, so what we showed, just one word, and then I'll finish. We showed that this is the volume plus a correction term plus a power saving, and this correction term is quite interesting. It's actually there. You can't get a power saving without a correction term. It comes from vectors which are almost very close to being isotropic, and that sort of, and also subspaces which are very close to being isotropic. There is a correction term you have to put in order to get a power saving. Okay, thank you, and sorry for going over time.
Say one word why you stuck in right 2.
So in this feature, so it's sort of between the lines, this trick that I described, this way of getting from in the spherical case of it sort of also works in this direction. So somehow points which differ by the SL2 orbit basically would have the same behavior under this type of unipotent orbit. So essentially, it's a 5-dimensional problem. So essentially, and then you sort of look, let's say, on the Lie algebra level at the adjoint representation. So for these generic unipotents in rank 2 groups, it's SL2, which you could ignore, plus an irreducible representation. A reducible case is sort of more complicated. It's not hopeless because, for instance, Young did it in this case of singular unipotent. But it certainly adds complication. So that's basically the cases where you have a unipotent which acts in that this representation becomes irreducible. That's sort of the case. Yeah. So one thing I should say, and sort of maybe this is, so we began thinking about this for many years ago, and there was an obstacle which was obvious to us in that there are sort of there's this Mastrand projection theorem, which I like very much, but it requires some transversality in the family of projections. And I remember talking with Bourgain about this, and it sort of was completely unclear what to do with families of projections which are not transversal until there was a breakthrough paper by Kanmaki, Oppenheim, and Venieri, which used Schlag and Wolf technology. And then completely different technology. So Gan, Goose, and Maldag, and Gan, Gao, and Hong Wang were able to use decoupling to prove these projection theorems. So these projection theorems that I haven't mentioned are sort of a very important ingredient in what we're doing.
What kind of different condition is
Hmm?
needed? What kind of Diophantine condition?
So yeah, it's sort of the Diophantine condition that we need for quadratic forms is the weakest sort of reasonable one. That for some power, the difference between my quadratic form and the integer quadratic form in sort of the projective sense would be bigger than a constant times the determinant of the integer quadratic form to an arbitrary power. Okay, so it's sort of a condition that effectively follows from Liouville bounds or something if your rational form was given by algebraic numbers.
Non-arithmetic case, you mentioned you have these issues with these orbits. So I remember there's this paper of, I think, Einziedler, Margulis, and Venkatesh, where they have polynomial equidistribution for periodic torus orbits. And there was some discussion by Venkatesh, I remember, about if you have non-periodic, non-closed orbits, there was some issue with getting this rate. Is it the same sort of situation that you have here? The same
No. That paper uses very, very strongly this remarkable fact that for families of periodic orbits of arithmetic groups, they use that it's a congruence lattice, you have a uniform spectral gap. And that uses serious arithmetic input. That's sort of not relevant here.
I'm just saying the issue with extending it to non-periodic orbits, is that a related issue here that you might be somehow, no, you're saying it's totally different?
It's different, it's not related. As much as things can be unrelated, I mean,
Before we thank the speaker again, there'll be 2 more announcements after.
and we need to thank the organizers. And this, I'm not sure that you can do that. So I'd like to thank Nick and he and Alex Gambold and Sound and Actec for this wonderful conference. thank all of the staff, that some of them are here and most of them are not here, but maybe they see the recording to catch up on what they missed, for arranging this meeting. And last but not least, to Peter being the occasion for this celebration. So thank you, Peter.
Okay, the first announcement is not mine, but is Mayank here? I think there's an announcement about a shout out. Just
there's a cricket game that will be happening and being organized at 2. So we'll be gathering here at 2 and then
okay, cricket game at 2. If you didn't hear that, you can ask Mayank up there. And so finally, I just wanted to thank all of you for coming this week. We had many wonderful talks, but it's not just the talks that make a good conference. I don't think we could have asked for a more engaged and interested audience than we had this week. So thank you all, and I wish you a safe trip home.